Hello. Our work focused on the growing volume of solid waste being generated from the investigation, treatment of groundwater resorbents or granular activated carbon or GAC, and excavations of PFAS-contaminated soils. Our study examined the application of smoldering combustion to destroy PFAS. Smoldering is a flameless combustion process, but its key advantage is that it's very energy efficient, and once initiated with a small energy input, it is self-sustaining if the fuel remains in air supplied. It's an exothermic combustion reaction that will convert carbon compounds to carbon dioxide and water. It does require porous media, an organic fuel, and air. Smoldering does rely on the combustion triangle that requires all three things, fuel, oxygen, heat, to be present in the same location. Barbecuing with charcoal briquettes, which are both a porous matrix and a solid fuel, is an example of smoldering that you'd be familiar with. As you know, you can use a small electric heater or a bit of starter fuel and a match to start. Once initiated, the briquettes glow red hot, giving off lots of heat and ending when the fuel is consumed and only ash remains. We do the same thing when we use this commercial process to treat hydrocarbons, because they'll behave like a barbecue when embedded in a porous matrix. Our fuel is the contaminated soil itself that is embedded or added to a porous matrix, such as sand. Our oxygen is the oxygen we inject. We start the process with a short duration energy event. After ignition, we can take away the heat, and the energy released during smoldering of the hydrocarbon is trapped by the sand and recycled to cause the adjacent hydrocarbons to form a solid phase char, and raising it to its ignition point. Combustion happens on the surface of the solid fuel as long as we keep supplying air, and the smoldering front will migrate in the direction of the air in the porous medium. Treating PFAS requires heat if we're going to thermally destroy it, and basically that will form hydrogen fluoride that's mineralized and potentially shorter chain compounds. We know the mineralization starts when the temperatures get beyond 700 degrees Celsius and starts maximizing the mineralization as we achieve temperatures greater than 900 degrees Celsius. However, PFAS is not a great fuel for us to smolder. Often it's present at too low concentrations to be effectively smolderable. And as well at really, really high concentrations, we may eventually snuff out the actual smoldering reaction because it'll block air transport to the surface of the fuel. So we need to add a surrogate fuel into the porous matrix to make this happen. So what about spent GAC? This is the original concept we started off with. The idea that, well, it's a potential waste product that contains PFAS. So we would figure that if we could add this GAC as a solid phase into the soil, we'd basically treat both PFAS on the GAC and also any PFAS is on the sand itself. So basically, our fuel is now going to be soil plus PFAS, but GAC. So the key project phases to go through this process was first lab column test to really focus on fluorine mass balance, and also we investigated the application of calcium oxide as to enhance the demineralization of this process and also cause removal of the hydrogen fluoride, forming calcium fluoride as a way to minimize hydrogen fluoride emissions. And then we tested this at a larger scale in a pilot test looking at heterogeneity and to show that it could be field deployable. Our lab column results were very, very promising. With very little addition of GAC to the soil, approximately 50 grams per kilogram of soil, we could achieve temperatures greater than 900 degrees C and even achieve up to temperatures of 1200 degrees Celsius. Looking at what was left after treatment, we found that there's a 99.9% and greater reduction in the detectable PFAS and often below detectable limits. We also used particle-induced gamma emission to look at what was happening to the fluoride in the system and also maybe emitted in our emission traps. And we again found that there was also reduction of F mass, the total mass in the system, in instances without calcium oxide amendments. However, there's no change in the total fluoride concentration with calcium oxide present. That's because we're getting the formation of calcium fluoride, which was proven out by the use of XPS and XRD to verify that we're getting the formation of calcium fluoride. We also found that there was very little F mass being emitted, even as PFAS compounds or breakdown products, less than about 0.1%. And then we also found that with calcium oxide soil amendments, we had a lower F mass on the emission treatment GAC, which is consistent with less hydrogen fluoride being produced and shorter chain compounds being produced as well. And we had excellent mass balance. Without calcium oxide, we had a range of 68 to 109% associated with the fluoride that's in the system. But with calcium oxide, we had generally better mass recovery. And the difference is it really is a function of like the uncertainties with respect to the measurements of initial amounts we put into the system, as well as analytical uncertainties. Our pilot test was conducted at Canadian Force Base Trenton using our 10 cubic meter pilot scale hot pack systems. This located on the right of the screen is basically a container that has a plenum area for air distribution and also to hold the heaters that we use to initiate the process, as a retractable roof and also a door, which allows us to seal the system in, and we can collect the vapors for analysis and also for treatment. We used AFFF soils that were stored on the site and contained a mixture of different PFAS compounds as well as any other hydrocarbons that may be associated with the fire training area. We were very excited by our pilot test results. Our soil results showed that we had over 99.9% removal of the targeted compounds, and often many of them below the detection limits. The XPS confirmed that we're getting formation of calcium fluoride in the soils. We also, based on the emissions, we could show that only about 0.2% of the total fluorine was emitted as a PFAS compound that was captured in the emission tubes, where about 1% of the total organic fluorine was emitted as hydrogen fluoride. The low amount of fluoride captured in the system is consistent with the application of calcium oxide, both removing the hydrogen fluoride and improving the mineralization. We only detected 6.2 FTS in the condensates at very, very low concentrations. We collected about 600 liters of condensate per test. We did also collect a solenoid canister gas analysis, looking at see if we're missing anything that could be coming off. We did detect 6 fluorinated compounds. 4 of those compounds were also detected in lab air. And so we were left with 2 compounds, and they tend to be long-chain hydrocarbons with a phenyl group their fluorine atom has been attached to. So they were very poor or fair matching in terms of these compounds, and so more work has to be looked at, particularly to what potential byproducts could be coming off during smoldering or other thermal treatment reactions. And basically, though, anything that does come off the system, it could be treated by typical air treatment using granular activated carbon. And of course, we could then use that granular activated carbon to actually feed into the next batch and both treat that carbon as well as treating any soils with PFAS. In summary, we have a very effective and robust treatment system. We have a great understanding of the PFAS that happens during the smoldering. We have good mass balance, a good understanding of what happens to the fluoride. It's a simple process and allows on-site treatment. There's a high contaminant destruction efficiency. We get minimal products of incomplete combustion being emitted. We can treat co-contaminants in addition to PFAS. And it's a very safe and sustainable process, and it's all because we basically use less energy. And we are very pleased that we were also awarded in 2021 Project of the Year for environmental restoration. Thank you.